finish doing the survey, you can turn it back to me. And also that I'm distributing these colorful flashcards for you to have for you to answer questions in class, so that you come to the front and take one of each color, including the white. Okay. Take on each color.
And then we'll get started as soon as possible.
Just out here, they're also doing a student background survey. So that pick one, fill it out. Also take the one the colorful card at the front.
Ah. Okay, we have wasted 17 minutes. Huh? Okay, now let's get started. Sorry about the mess up of the time of the classroom. I assume that you all received my announcement last night about the class, correct? Yeah, you got an email from I think. And so that, you know, I said the classroom is in LT2, but actually it is in LT1 for today. Now I have to double check whether it's actually in the other room on Thursday. I think that may be the case. So what I listed in the syllabus is also incorrect. Sorry about the mess up. So this is a class UD General Education 2401 D, section D for astronomy. And I'm a teacher, Renbin Yan Renbin in Chinese. Yan is my last name, my family name, and Renbin is my given name. We also have two teaching assistants. Let me try to find the pointer here. Anya Liu and Samantha Burrell Tapam, they are graduate students in the Department of Physics. I'm an associate professor. This is actually my first year at CUHK, which is why I messed up the time. I didn't know that it's possible for a single class to have two different classrooms on different days. Before I came to CUHK, I was a faculty at the University of Kentucky for 9 years, since 2012 to 2021. And before that, I got my PhD at the University of California at Berkeley, where I studied astrophysics. And before that, I was an undergraduate student at Duke University. So I loved astronomy since I was little, and I studied physics and astrophysics. And right now, besides teaching, I do a lot of research in astronomy, astrophysics. We do observational astronomy. We use big telescopes and put spectrographs on them and take images and spectra of galaxies. So I should use the microphone. Do you guys have trouble hearing me or not? For the people at the back, is this volume okay? Is it okay? Okay, then I'll just keep going like this, and then I'll figure out the AV password later on. during the break, maybe. Okay, so where I was. So I study galaxies. I study how galaxies evolve in the universe, and we're trying to understand where does the universe begin and how the galaxies form in the universe and how they evolve, and what kind of galaxies we live in. Those are the research that we do. And we use spectroscopy surveys. We do very large surveys, a lot of data analysis. But if you are actually interested in astronomy, you are also willing to, I'm also happy to talk to you. Also that right now at CUHK, we're also building astronomical instrumentations. We're trying to build new instruments that enable new capabilities to do astronomy, not the same thing as before. We always want to do new things. When we enable new capabilities, we can discover new things about the universe. The two teaching assistants, they are graduate students in the Department of Physics. They will be grading your homework, and they also provide consultations. So you can also go to them for office hours if you have questions. They are studying gravitational waves, which is a very cool thing in astronomy today. That just in the past several years, for the first time we detected gravitational waves from astronomical objects. And so they study those, so that if you're interested in gravitational waves, you are also welcome to talk to them. I have the syllabus on Blackboard, which you can see is under the course outline section on Blackboard. I will just now go through that too much. And now the class time is correct, but the classroom is wrong. I actually don't have it here. My office hour is right after class. It's basically after class on Tuesday and Thursday. The Thursday for today is 4:30 to 5:15, and then on Thursday it's at 2 p.m. And you can also email me to make an appointment if you have questions. And my office is in the Science Center, North Block 344, and that is there with the red ellipse there in the central campus, Science Center, North Block. And here are the emails and office hours for the TAs. Anya Liu right now is quarantining in a hotel, and so that you have to, for the January, if you want to contact her, you have to set up you have to do the office hours through Zoom. So here is the syllabus for this course. I just use the cursor as a pointer. So we'll cover many different aspects about astronomy. And this is a little different from other, I guess, from the astronomy that you are used to, probably. That in high school and middle school, you probably learned a lot about seasons, about the moon, about planets, the solar system. Those are the traditional or the classic astronomy that a lot of people teach. But now today, with so much technology improvement, we actually know a lot more about the universe. And there's a lot of exciting things that we discover that is far away from the Earth, from the Milky Way, deep in the universe and cosmology. So my class will be covering more topics in modern astronomy. We talk about a lot about stars and galaxies and the cosmology. So see that for the first few chapters, we will talk about the basic things, the scale of the universe, motions in the sky, so that you know how stars move in the sky, and how do we measure them, and why they move in the sky in that way, and why you see different constellations in different seasons, and the reason for seasons, phases of the moon and eclipses. Those are the basic astronomy knowledge. And then we talk about the nature of light and matter and how they interact, because light is the most fundamental tool that we use to study the universe. We cannot go to the stars easily, right? Stars are too far away. We can only see the light coming from the stars. So we observe those light, and then we analyze them. And that is how through which we understand the universe. And also that we want to know how matter produces light and how matter absorbs light. And that is through that interaction that we can understand the universe, what produces those light and why they produce those light, how they produce those light. We'll talk about the solar system, but we will not focus too much on the solar system. We talk about the sun, why the sun shines, and we also talk about the solar activities, the solar prominence, corona, and why they have sunspots and those kind of things. And then we'll go out to the solar system, go beyond the solar system, go to the stars. We talk about how we measure distance to the stars. Stars are very far away, but how do you measure how far away they are? And then what kind of properties stars have. And we want to understand, we want to tell you how stars evolve, how stars are born, and what kind of life they live, and how they die. And when they die, what kind of things they become. They become white dwarfs, neutron stars, or black holes. And what are those things? And then we talk about the Milky Way, the galaxies, and we go beyond our Milky Way and go to the more distant universe. We talk about quasars, active galactic nuclei, which are powered by supermassive black holes. And we also tell you why we think there is dark matter in the universe and what kind of things they are, and what is the Big Bang cosmology, and what is dark energy. You probably hear a lot of these words in the news or in all kinds of media, but what are these things really are? So that's the material we'll talk about. There's no textbook that is required for this course. I will assign some reading and some links on Blackboard that you can go take a look. Actually, for today's class, I also assigned some reading content. You don't have to read it beforehand. You can read it afterwards. That's all fine. And most of the sources are freely accessible, and so you don't have to pay anything. And there, if you really want a textbook, there is a textbook called Astronomy, and it's a open source, a free textbook online, and it's offered by OpenStax. They offer all kinds of free textbooks, and you don't have to buy these expensive textbooks because these astronomy knowledge are covered in so many books that we don't have to have them. There's so much online resource, and with these online resources sufficient for you already. And so you can use this online textbook if you want to, and I'll assign some chapters in those for you to read. But also, if you really want to have a hard copy of something, you can order this textbook from Amazon. I think that it's actually cheaper because it's open source. About the grading, it's really mainly composed of 3 components. There will be a midterm costs 30%, counts 30%, and the final exam accounts for 40%. And then there will be homeworks. There will be 6 homework sets, and in total they count 30%, and it adds up to 100%. The homework assignments, there will be bi-weekly. So every 2 weeks, we'll assign a homework assignment on Blackboard. And then it's mostly be multiple choice questions. So it should be very simple to answer. Just like the surveys you were doing, a few more questions than this. Maybe at most 20 questions at a time. But these are all really simple ones. And it's really based on just the class, the lectures I gave. And I'll put it on Blackboard and you print it out, and then you fill it in and answer the short answer questions, and then hand it in the week after. So every 2 weeks, there will be a homework assignment. And for example, the first homework site will be given out no later than Thursday of the next week. And then it will be due a week afterwards. So that will be due by Thursday, by the Thursday class on the following week. And you need to hand it in to me before the class. There will be 2 exams. A midterm will be, right now I tentatively scheduled it for 10th of March. It's a Thursday, because on Thursdays we have shorter lectures. We just have 1 session. And on Tuesdays we have 2 back-to-back lectures. And we'll have a break in the middle for the Tuesday lectures. The final exam date and time is still to be determined. And I want to emphasize that we don't tolerate any dishonesty for academic works, that no cheating, no plagiarism on your homeworks and exams, and work on your homework assignments independently, not in groups, okay? And with the first homework, you're required to hand in a signed copy of the declaration for a written assignment. And you probably have done this for other courses as well. You can find it in the last page of the syllabus, and then print it out and hand it in with your first homework assignment. And you only need to do this once. I'm not asking you to do it every time you're handing an assignment. So you only need to do it once. But remember to do this with your first homework assignment. But that should cover the whole semester, not just the first homework, right? It covers all the assignments and your exams. And you have any disability accommodation you needed, let me know. Classroom behavior, I think we are all good. Just respect each other, turn off your cell phones, and make sure that you don't interrupt other people's learning. Check your emails. If you all should have gotten an email from me last night, and probably just now as I changed the classroom or something for you. And if you didn't find the email, that means the email you got is probably not correctly registered. So fix your email registration to make sure you can receive emails from me. Okay, how to succeed in this course? Attend the lectures, ask questions, and take notes. The slides will all be posted on Blackboard so that you can use the slides to study afterwards. And make sure you study them. I will post a lot of questions in class. And actually, at the beginning of every lecture, I will post some questions to review the previous lecture. And a lot of those questions will actually get asked in your homework as well, and also in the exam. So as long as you study those review questions well, you should do really well for your homework and exams. And make sure you hand in all your homework. Okay? And I just hand out these flashcards. These are what I'm going to use to do in-class questions. So that you see these 5 colors, and they will always be representing A, B, C, D, and E. Okay. So pink is A, and yellow is B. Green is C, and orange is white is D, and orange will be E. So that if I pose any questions, I want you to raise these flashcards to me so that I can see who answered what. And so how many people are answering correctly and how many are getting it off wrong. The reason I'm using this is because it's very efficient, actually. It's very, very quick, and also I can see immediately. And also it is kind of private because on the back side is OI. No one else can see what you answer unless they try hard to look around, right? And so you just pose it, face the color side toward me or the white one, and I can see it. So let's just try that right now. Why are you taking astronomy? Show me your card. Which one is your reason to take this course? At school? Yeah, some of you are taking it just for fulfill requirements, that's fine. Hopefully that you will like it and you will start to enjoy it like many others who have taken this because of you're here to see the interesting astronomy pictures and facts. There's a lot of exciting things in the universe. There's many many things that sounds like miracles or very magic things, but they're not magic. It's actually physics. That is what works in the universe. It's physics. But those natural world sometimes give us so much wonders that the phenomena that we can see, once we start understanding them, we found they're so amazing. And that is the reason why I study astronomy. Thank you. So what's on my goal for this course? So for this course, I want to not only introduce you to these beautiful astronomy pictures, I want you to understand the amazing process behind it and how nature works. I want you to understand that. And nature is actually doing quite magical things in the universe. And that will help us, once understanding those, that will help us gain some perspective. And also I want to put the humankind and the earth into perspective. So just warn you, the next thing I'm talking about may not be good for your ego. What kind of picture is this? Actually, I should probably analyze this one. What picture is that? The picture of Saturn, right? It's a beautiful planet Saturn with beautiful rings. And this picture is taken by the Cassini spacecraft as it passed by Saturn and passed behind Saturn. So this is looking from the spacecraft, it's looking back toward the center of the solar system. The sun is right now behind Saturn, so that from basically the spacecraft is in the shadow of Saturn, and it's looking back toward the sun, Saturn and the sun. The sun is behind Saturn. Basically, there's like a solar eclipse from the spacecraft's point of view. That is why you see a ring, sort of a bright circle around Saturn, and this is the atmosphere of Saturn. So you can see here, this ring shines up. This is the atmosphere. And then these are the beautiful rings that is back illuminated by the sun. It's a beautiful picture. But this is not just a picture of Saturn. This is also a picture of the Earth. Where is Earth in this picture? You can't really see it from that angle, from that low resolution. You have to zoom in. And if you zoom in that little corner, and there's a tiny, tiny dot. And that tiny, tiny blue, pale blue dot is the Earth. Because it's very near the sun, it's in the central part of the solar system. From Saturn's perspective, it looks so tiny. That is the Earth. Everyone we know of, everything we have in the world is all on that tiny, tiny blue dot. And compared to the huge universe, it's just so minuscule, right? It's so tiny. And for us, the world is large, but in terms of the universe, that Earth is just so tiny a thing. It's like a piece of dust in the universe, in the dark universe. And so, right, that's tiny, right? It's like we are all crowded on this Earth. It's just like a living conditions in Hong Kong, right? It's a big city, but you live in a tiny apartment. But that's what we are doing in the universe. So that's a sense of perspective I want you to gain through this course. This is not the only example. There are many other examples later on. And also, I want you to learn how science really works, right? You see a lot of depictions about how science works in the media, in movies, in TV shows. There are many shows about scientists and how they make evil things sometimes. And a lot of those depictions are actually not correct. And so we want to tell you what science really is and how science really works. And we'll tell you through a conceptual way. This course is not very mathematical, okay? that we'll mostly talking about conceptual stuff. So through those conceptual stuff, I want you to practice your critical thinking skills. For some of you, this may be one of the last science courses you'll ever take before you get a job, right? And so critical thinking skills are very important. It's actually one of the skills that is highly valued by employers. What are critical thinking skills? Critical thinking skills is the ability to think independently based on facts and logic. Right? You don't want to just believe whatever others are saying. You need to think independently. You need to make logical derivations of from facts to derive what you think is the conclusion. And that is critical thinking skill, and that is very important. So that from this course, hopefully you get some practice of that skill. Okay, that's a goal for this course. And so I want to tell you, why do we study astronomy? Why are we interested in the stars and the universe? How many of you have ever looked up at the sky? I assume that you all have looked up at the sky, right? Have you looked up at the sky in Hong Kong? Have you ever seen stars in Hong Kong? Rarely, right? It's so Hong Kong has so bright city lights. It's actually very difficult to see stars. But when you were a child, when you were children, you probably all looked up at the sky at some time, and you probably all have seen stars before, right? So here is a picture of the Earth at night. You see bright city lights, and among huge areas of darkness. Where is this? Which part of the Earth is this? Can you figure it out? Asia? Where in Asia? China, right. You can see that this is centered around China. So there is Beijing. And here is Shanghai. Where is this? This is Hong Kong. This is the Greater Bay Area, and we are at the bottom of the Greater Bay Area. Oops. Yeah, so you can see this shape, but we are all living, most people live in big cities, and nowadays it's getting harder and harder to see the stars because the city lights are so bright. In Hong Kong, I have seen stars, but not many. You cannot see very many stars because the city lights are so bright. The sky is brightened by the city lights. And quite often it's cloudy, like this picture is showing. And even when that is happening, you can't see stars either. You have to wait for, go to a dark place, go to countryside, in a dark, remote, far away from cities. And when it's a clear night, you can see beautiful stars. And this is how I got into astronomy, how I got interested in astronomy. When I was little, I live in Beijing. I come from Beijing. And there you cannot see many stars in Beijing either. But when I was little, my parents took me to a camping trip on the outskirts. And at night, we see beautiful stars. I was shocked to see Milky Way. And it's so beautiful. It looked like this. Just kidding, right? That's a picture by Van Gogh, Starry Night. And this is more like it. This is the Milky Way. How many of you have ever seen the Milky Way with naked eyes? 1, 2, good. But most of you haven't. So you need to go find an opportunity to go out hiking or camping, camping in the countryside, or just go to a relatively underpopulated place when the city light is not so strong. And then you go out at night and you can see beautiful stars. Milky Way is really beautiful. And when you see thousands of stars in the sky, you will be amazed. And I guarantee you. And if you ever go to the southern hemisphere, that's even better. The southern hemisphere has much better sky views than us in the northern hemisphere. The southern hemisphere faces the center of the Milky Way. where you actually can see a lot of beautiful nebulas with your naked eye. So the Milky Way is not just yellowish or silverish. It actually looks, you can see red dots in it and dark patches, and it's much, much more beautiful. So if you ever go to Australia or New Zealand or Chile or any part in the southern hemisphere, remember to go out at night to see the skies. So that's why we study astronomy. We are curious about astronomy. So everyone, like our children, have seen the stars, and we are all curious about what's out there. And that is why astronomy is one of the oldest and the most fundamental science subjects. Ancient people started studying the stars from very beginning, right? So that's why you see astronomy-related architectures in ancient, from ancient cultures. This is Stonehenge in England. These big rocks are probably some kind of religious ceremonial ground. And the stones are aligned with the motions of objects in the sky, with stars. And basically the stones are aligned with where the sun is rising on spring equinox. And why do people do that? Because they studied, right? They looked up at the sky and they observed it every night. And then they figured out what is going on. And so they build these, they're so amazed by that, or sort of they're shocked by the natural wonders, and they build their architecture around these astronomical phenomena. Like the Mayan pyramid, it's also perfectly aligned with the positions of the sunrise on spring equinox. In our ancient Chinese culture, there's also lots of records about astronomical phenomena. We recorded all the eclipses and also the signs of comets in ancient Chinese literature, historical record. And this is a coin, an ancient Chinese coin. And on the coin, you can see depictions of Milky Way. That is the span in the middle. We actually call it Silver River in Chinese. And in the Western world, it's called the Milky Way. So that's a common name that is adopted now. And then you can see Venus. You can see different constellations, the Big Dipper, Sagittarius, and also here is the constellation that that have the star, bright star Altair, and this is a constellation have the bright star Vega. And these two stars are the two stars that represent a lovely couple that got separated by the Milky Way. There's a lovely romantic story behind it. This is, if you know Chinese, this is 牛郎织女. Vega is 织女星, and Altair is 牛郎. And so we see astronomy in all Asian cultures. And the reason that astronomy has been studied by humankind from the very beginning is because we are curious about what they are and where are we from, right? How these stars relate to us. And actually, we have an intimate connection with the universe. We want to understand where do these stars come from, where does the universe come from, and where are we from, and what is out there around us, what is out there beyond the solar system, and are we alone in the universe? Are there aliens, right? You're probably interested in that question as well. And in the ancient times, you cannot study much, but today we have the technology. We have built powerful telescopes, and not only optical telescopes, but also radio telescopes, X-ray telescopes. We have also built gravitational wave detectors. We have many ways to study the universe now. And now we can truly understand what is going on in the universe. And that is a quite amazing thing, as you will see. And so what will we learn in this course? I'll try to give you a flavor of what we'll see. We talk about the sun. Here is a picture of the sun. This is not like any other picture of the sun they have seen before, right? This is a picture of the sun not in the optical light, but in ultraviolet light. And in ultraviolet light, you can see the sun is actually not that bright. You see a dark disk. And on top of the dark disk, you see these bright spots. And these bright spots are signs of strong activities on the sun. There are these magnetic field lines, and they're hot plasmas that are interacting. And that is almost having explosive actions at those spots. And that is why you have these really bright spots, bright points. And this is a picture of the solar corona. The sun is not actually that peaceful. I mean, it looks peaceful to us, but actually there's violent activities going on the sun all the time, every day, and actually affects us. That's the sun. We also talk about stars, and we talk about the structure of our Milky Way galaxy. Milky Way galaxy is made up by hundreds of billions of stars. And there has been a recent huge advancement in studying the structure of the Milky Way. European Space Agency launched a satellite telescope called Gaia, this little thing on the right. And it launched about 8 or 9 years ago, and has been providing very accurate measurements of positions of stars in the sky. And from that, we were able to tell the distance of the stars. I will tell you how we tell the distance of stars. We actually measure the distance of the stars using parallax. I'll tell you what that is in this semester. But that is a very simple principle. And this satellite used that very simple principle to make very accurate measurements. And it was able to map a huge number of stars in the Milky Way. So we can figure out exactly how they're distributed. And that tells us what the Milky Way is like. And also that in recent years, you have heard about gravitational waves. And in 2017, on August 17th, 2017, for the first time in human history, we discovered a binary neutron star merger and the gravitational waves that are produced by the binary neutron star merger. This is an animation made by NASA. 2 neutron stars merging. It's a very cool animation, and it is actually showing a very, very realistic picture of the process when 2 neutron stars merge. And this, before we discovered this, we know we have theory predict this is going to happen, but we have never observed it. And in 2017, we observed the first time the 2 neutron star merge. And when the 2 neutron star merge, they created that huge cloud. And in that cloud, heavy elements are made, heavy elements like platinum and gold. These elements that we use in our jewelry, right? These elements actually are all made in neutron star mergers. So if you ever wear a gold ring or a platinum ring, you know that actually comes from neutron star mergers because there's no other way to make them. So the ring on my hand, this is the remnants of neutron star mergers from ancient past, somewhere in the universe. There was neutron star merger before the sun formed, and so that the gold that was made in the neutron star mergers actually get distributed in the universe. And when the sun formed from those dust that is produced by neutron star merger, we can have these kind of elements in our solar system. And when the Earth formed, you have gold on Earth, right? So you can see I'm wearing neutron stars on my finger. So these are amazing facts. This is a picture of the black hole. This is also one of the first things that happened in the past few years. We live in a very exciting era of the humankind. We actually, for the first time, know a lot more things about the universe than our ancient ancestors. This is a picture of the black hole taken by the Event Horizon Telescope. Black hole, you think the black hole doesn't emit any light, but why is there light around it? These are the material that is falling onto the black hole. As they fall into the black hole, they become really hot, and they start emitting light. This is the ring of light that you're seeing around the black hole. We talk about black holes. Also talk about where do we come from? Big Bang. How the universe start? You probably all have heard about the word Big Bang, maybe from the TV show Big Bang Theory, right? And what is the Big Bang? Big Bang means that at the very beginning of the universe was intensely hot and really, really dense. The density goes to infinity, and everything is cramped together. And at that time, you can't even have atoms. You can't even have electrons, or you cannot have normal matters. But there was expansion, fast expansion of the universe. The universe expanded by so much that the universe actually cools down. And when it cools down, atoms can form, electrons form, and hydrogen, helium, these kind of elements can form, which actually made stars and galaxies and us. And so that is the sort of a history of the universe. We'll talk about how we know about this and what is going on at the beginning of the universe. We'll tell you what the universe is made of. We are made of protons and neutrons, these what we call normal matter. But most of the universe is actually not made by normal matter like us. Most of the universe we now know is made of dark energy, some mysterious force out there that we don't really understand its nature. But we have evidence for its existence. And I will tell you what those is. I will tell you dark matter. Dark matter is also a major component of the universe. 26% of the universe matter is dark matter. What is dark matter? Dark matter are not like us. We cannot really see them. We cannot even sense them. We cannot feel them. They don't interact with us. They actually exist in this room. They may. We think it's some kind of particle, and it's like a ghost going through the room, and you can't even notice them. They penetrate you through and you don't exist. So these are dark matter and dark energy. But we'll talk about this later on, and we tell you what we are made of. Where do the elements that make us come from? What elements make us? We are made of 70% water, right? And then we have flesh. And what makes our DNAs? What kind of elements are there in there? At the beginning of the universe, there is only hydrogen and helium. The Big Bang only makes two kinds of elements, hydrogen and helium. But we are not made by, there's hydrogen in water. But there's also oxygen atoms, right? There's oxygen that we breathe. There is nitrogen that make up our DNA. Our DNA have nitrogen in it. We have iron in our blood, right? Where do these elements come from? And carbon that make up our bones. These elements are actually not made at the beginning of the universe. They're made in the cores of stars. So at the center of the stars, where nuclear fusion is happening, they can turn these light elements into heavier elements: carbon, oxygen, nitrogen, iron. These elements are all made in the centers of stars. So the stuff that make us was once in the center of the stars. Can you believe that? So that you are actually children of the stars. Me, I'm also children of the stars. All of us are. So whatever that is on Earth, most of these things are actually once in the center of stars. And when stars explode, these things get distributed into the universe from which the sun and the Earth can form. So that is what we know about what I want to tell you throughout the semester. So let's just give you some flavor. Okay, so that's a first lecture I have, and And I think we can take a little break now, and maybe let's take a very short break. So that since we have lost a lot of time at the beginning, maybe let's see, 45 minutes till the end of the class. So that let's take a 5-minute break. Okay. And come back at 3:35. Thank you. Yeah, it's on the Blackboard. Yeah, yeah, you can download it from the Blackboard. Yeah. Okay, let's get restarted. I hope this microphone is working now. Is it? Can you hear it from the microphone? Okay, so I don't have to keep yelling. So this second class, we want to talk about the scale of the universe. And there's no better thing to talk about the scale of the universe than using the context of possibilities of cosmic collisions. Cosmic collisions are what I mean collisions between galaxies and between asteroids. And you probably, in a lot of sci-fi movies, you have seen collisions of asteroids colliding with the Earth. And actually, that can happen. That has happened before, and that's what killed the dinosaurs, right? And you can also imagine that there may be collisions between stars. I was saying there was neutron star collisions too. And so, how likely are these collisions? Is it collision between galaxies more likely? Or is it collision between stars and between planets and asteroids? These are all cosmic collisions. Which of these collisions are more likely to happen? That's the question I'm posing right now. You can take a guess. Think about which possibility is higher. Raise your card to the corresponding color. A lot of you are choosing asteroids colliding with the Earth. Few grades and yellow. Okay. Remember your choice, and then let's see. I'm not going to tell you the answer yet, and we'll see how we make that judgment. So don't put it away your card yet. Which of the following situation is more likely to have a collision? A crowd of people party together, and that is a baseball field with baseball players. That's assuming they're not just standing still. That's assuming that these people are just running around randomly. Just like if you blindfold everyone so that they cannot see, and then you ask them to run around. It's very obvious, right? I think some of you are showing me which one it is. Apparently, it's situation A, right? That case one where people are standing around each other. That is more likely to happen, to have a collision. What about this case? Now it's all on baseball fields, very large field. In situation A, I have just a few players. And in situation B, I have these huge, gigantic balloons. Which case is more likely to have a collision? You have either the players going around or just have these giant balloons going around. Too obvious to worth showing. I think you all know, right? It's this possibility B. Sorry, it's situation B. And because, why is that? Why is this case, the balloons are more likely to collide? Why is that? Anyone want to say? Just say it out loud. Because they're bigger, right? Because they're so big. So that it's very easy to run into each other. And the small players are so tiny compared to the field when they run around, they'll likely miss each other, right? And so that means that not only the density, the distance between players matter, the size also matters, right? And in the first case, the reason that crowd is so likely to have a collision is because they are so close to each other. People are so close to each other. And in this case, the players are so far away from each other, so that distance between them is causing the difference in a collision likelihood. And in this case, it's the size of objects that is causing a difference in the collision likelihood. What about this case? Now it's actually two different fields. The first field is a bunch of balloons, not that big anymore. On the baseball field, a bunch of middle-sized balloons. And then in this case, I have a basketball field. And let's say that they're not just playing basketball. When they play basketball, of course they will collide. But you have to say, okay, stop playing basketball. Blindfold, cover your eyes, then run around. And how likely are they to collide? Or how likely are they? Which one would be more likely? I think more of you are saying B, but some of you are also saying A. It's actually very difficult to judge because the balloons are more far apart, right? But they're also bigger. In the second case, the field is small. The basketball field is much smaller than a baseball field, but the player is also smaller. So it's actually very difficult to judge in this case. So the likelihood of collision depends on several factors. It depends on distance between objects, right? It also depends on the size of objects, as I was saying. And actually, there's a third thing that it depends on. It also depends on the motion speed of objects. How fast are they moving, right? And if they move faster, it's easier to collide, actually, because they have more chance to get near each other. But if they're moving really slowly or staying still, then they will collide, right? So all of these factors matter for evaluating the possibility or probabilities of cosmic collisions. And we'll ignore the third factor for now when we talk about cosmic collisions just for the moment. And so the key things that determines the probability of cosmic collisions are how the size of objects compare to the distance between objects. We'll evaluate how the size of stars compares to the distance between stars, and how the size of galaxies compare to distance between galaxies. I'm telling you that galaxies are system of stars. So actually, they're much bigger. But the distance between galaxies is also bigger. So we're going to evaluate which one is more likely to collide. Which kind of collisions happen more frequently? We need to compare the sizes of stars to the separation between stars, and compare sizes of galaxies to the separation between galaxies. And so that we need to get some sense of how they compare. I'm going to give you the numbers later, and then I'm going to tell you how we can evaluate, how we can do that comparison. But before we do that, we first have to talk about what are galaxies, what are stars, and where are we in the universe. This is a very fundamental, the very first thing we have to say. What are we talking about? So we start talking about our address in the universe. And when we give out our address, it's just like giving, let's say, there's an alien that asks you, where are you? Suppose you make communications with the aliens. How do you tell the aliens where are we? What is our cosmic address? And our cosmic address can be just given in a similar way as we give our postal address. That when you're trying to receive a delivery, you need to give the vendor, the online store your address, right? What is your address? And let's first look at where we are on Earth. And in giving our address, there are actually two different conventions in China and in the Western world. In China, we always start from the big things to the small things, right? We start from the country, and then the province, and then the city, and the district. But in the Western culture, it is usually going from the small things to the large things. Since it's given in English, we'll just follow the English convention for now. Where are we on Earth? We are at CUHK campus. We have a beautiful campus. And where is UHK? it's in the district of Sha-Tian in Hong Kong, right? And that is the boundary of the Sha-Tian district, and we are right here in Ma Liao Shui. And that's where we are. And then where is Sha-Tian? Sha-Tian is a district in Hong Kong, right? And this is a map of Hong Kong. You can see this is where Sha-Tian is, and our campus is right there. And then where is Hong Kong? Hong Kong is part of China, and is this little place in the huge country. And then where is China? China is part of Asia, right? And this is a map of Asia. And where is Asia? Asia is on Earth, right? You can say so. And so you will describe our address to someone, maybe an alien, okay? Describe it to an alien who doesn't know where we are on Earth. And you can say, okay, we are in CHK, and which is part of Sha-Tian, and Sha-Tian is part of Hong Kong, Hong Kong part of China, Asia, and then Earth. So this is sort of the order that you will give our postal address, right? And what about the cosmic address? What about the Earth's cosmic address in the universe? Where is Earth? What is the next thing? Say it out loud, please. You know, solar system, right? That's pretty simple, right? We have the sun, that is the central star in our solar system. We have 8 planets going around it, and Earth is the third one away from the sun. This tiny thing in there. Actually, this is not a scaled model of the universe, okay, of the solar system. This is actually exaggerated. We are not that close, and we're not that big. And then where is the solar system? Solar system is part of the Milky Way. Our sun is only 1 out of 400 billion stars in the Milky Way. There are 400 billion other stars in the Milky Way, just like our sun. And each of them, many of them also have planets around them. And so there are many, beside our solar system, there are many other star systems that have planets. And we are just one of those 400 billion of them. And that is our current understanding of the Milky Way. The Milky Way has a very, very dense center. The stars are more crowded there, relatively speaking. And our sun is somewhere there. We're not at the center of the Milky Way. We're actually living in the suburbs of the Milky Way. We're about 25,000 light years away from the center. And our solar system is actually at that place in the Milky Way. And where is the Milky Way? There are actually many other galaxies like our Milky Way in the universe as well. And they're just beyond the Milky Way, there is a few other galaxies. And these galaxies make up what we call the local group of galaxies, or the local group of galaxies. Yeah, local group for short. So you can see in the local group, there are actually 2 big galaxies. The Milky Way is here. And then another galaxy is about the similar size as our Milky Way is the Andromeda galaxy. This is our Milky Way, that's Andromeda. And then there are a bunch of other small galaxies out there. There's 2 small galaxies called the Magellanic Clouds. And these are dwarf galaxies very near our Milky Way. If you go to the southern hemisphere and look up at the sky, at night, if it's perfectly clear, you still can see these 2 kinds of blobs, like 2 clouds. This is when Magellan first going around the Earth, they actually named these clouds Magellanic Clouds. They're probably not the first person who sees it, probably dolphins or someone who actually sees the Magellanic Clouds first. But it's actually 2 dwarf galaxies next to the Milky Way. And so you can see the local group here is made up by Milky Way, Andromeda, and a bunch of smaller galaxies. And these smaller galaxies also have hundreds of millions of stars in them as well.
And where is the local group? So Milky Way is part of the local group. And where is the local group? Local group is part of a much bigger structure called the local supercluster. Supercluster of galaxies. So in this plot, every little dot you can see here. These it's hard to see that, right? But every little dot in here is a galaxy, and each of that little dot contains hundreds of billions of stars in them, and those stars all have planets around them. And this is a local group right here. A local group is in this place. And this is called the local supercluster. You can see there are several, it's actually made up by several galaxy clusters together. You can see there are some regions that are fairly dense. This is the Virgo cluster. It's made up by thousands of galaxies. And this is the Fornax cluster and Eridanus cluster. So these clusters are much more denser regions than our local group. Our local group is actually not in a dense galaxy cluster. It is also kind of like in a suburb area of the local supercluster. We're not at the very centers of it. But anyway, the local group is part of the local supercluster, and local supercluster is part of the universe, a network of galaxies. This is what the universe looks like on very, very large scales. Each little dot in here is a galaxy, and when you plot them all out, they look like it's like a network of galaxies. It appears like they all trace out these filaments, and then there are these clusters of things where you see a little bit more denser regions. Those are the galaxy clusters, and our local supercluster is part of the universe on very large scale. So this is our cosmic address. We say, where are we in the universe? We say, okay, Earth is part of the solar system. The solar system is part of the Milky Way galaxy, and Milky Way is part of the local group, which is part of the local supercluster, and we are somewhere in the universe. Okay, that's where we are in the universe. And now we're ready to talk about the scale of the universe. We need to talk about the scale of space and also the scale of time. So I want to give you these important perspectives. And for that, we need to use scientific notations. I want to see how many of you can write this correctly. Okay, so astronomy uses a lot of large numbers. Large numbers are very difficult to write if you just write it completely all out. For example, we talk about 400 billion things. I was just saying the Milky Way has 400 billion stars. What is 400 billion? 1 billion is 1 followed by 9 zeros, right? And 400 billion, you have to add another 2 zeros in there. And so that's 100 billion. So that's a very large number, 1 followed by 11 zeros. How do you write that in a simple way? So we invented this way of coding using scientific notations. For example, simple numbers like 10, we can say it's 10 to the first power. It's like just 10 by itself. Okay, there's only 1 10. And if you say 1,000, 1,000 is 10 multiplied by 10, and then multiplied by 10 again. So you have 10 times 10 times 10, 3 times together, right? That gives you the 3 zeros after the 1. So that in scientific notation, we don't want to write too many zeros. What we do is just to say 10, and then put the 3 to the upper right. And that is what we call scientific notations. We call it the 10 to the third power because there are 3 zeros there, so that it's 10 to the third power. And this is what we also say kilo. You say kilometer, it's 1,000 meters, right? And also in this scientific notation that we also write 1 in a special way. We just say 1 is 10 to the 0th power because there's no zeros after the 1. So there's just 0 in the exponent. And what is a million? A million is 6 zeros. So that we just write it in 10 to the 6th power. And a billion is 10 to the 9th power. And a million is a mega. And a billion is a giga. So you probably hear gigabytes when you talk about storage of your cell phones, right? How many gigabytes you have? That's it. How many 1 followed by 9 zeros are there, right? Right. A gigabyte is 1 billion bytes, and that is 1 followed by 9 zeros. So it's 10 to the 9 is a gig. We also use scientific notation to describe very small numbers. And just if you say it's, well, how do you write 0.1? 0.1 is 1 divided by 10. So that's so since you're taking out of a 10, so then this becomes -1 power. And you can see this is 1 is to the right of the dot, so that this is negative sign on the exponent. And 0.01 is 10 to the -2 powers. And if you try to write this tiny, tiny number, you can write it in a simple way. It's 10 to the -10 power because the 1 is a 10th digit to the right of the dot. And you count there's 9 0 here, and 1 is a 10th digit, so that is a 10 to the -10. So this is how we write scientific notations. And if any numbers I give you, they are for astronomy. Usually, it's written in these scientific notations. And we don't need to use this kind of math too much in this course. So if you're not familiar with that, don't worry. I think most of you are fine. But some of you may not be that comfortable with math, but that's fine. We'll use these numbers, but I'm not going to test you very much on that. This class is mostly conceptual. And this is how we write numbers that is not 1 in the front. If it's 2,000, it's 2 to the 10 to the 3rd power. And this is 5,400,000. And we write it in 5.4 times 10 to the 6. Because you look at the first number that is not 0, and that is determines what is exponent. And since 5 is on the 7th digit, there's basically 6 digits after it. And so it's 10 to the 6. And this is how you write small numbers, 0.023. The first number that is not 0 is on the 2nd digit after the dot. So this is 10 to the -2. And then you just put the dot right after the first number that is not a 0. So it's 2.3 times 10 to the -2. Okay, why we use scientific notations? Because it's very difficult to write very huge numbers. If I ask you which of those numbers are bigger, can you tell me immediately? No, right? It's so hard to count how many zeros are there. But if I write it in this way, I say the first number is 1 times 10 to the 21st power, and the second number is 1 times 10 to the 20th power. It's very easy to tell which one is bigger, right? This one has 21 zeros after it, after the one that has 20 zeros. Of course, with more zeros, you have a bigger number. And that's very easy. And also scientific notations are making calculations easy. You want to compute these large multiplications. We don't have to count how many zeros are there. We simply add the exponent together. So if the first number is 10 to the 8 and second number is 2 times 10 to the 18th, when we multiply them, we multiply the numbers in front of the multiplication signs, and then we just simply add the exponent together, and that gives you the answer, and it's very easy. So 8 plus 18 is 26, and so you have 2 times 10 to the 26. And when you divide them, you divide the numbers, And then you also divide, you subtract the exponents. So 6 times 10 to the 12 divided by 2 times 10 to the 8th. You just take the 6 divided by the 2, you got 3. And then for the exponent, you have 10 to the 12 divided by 10 to the 8th. And that is, for that, you just simply subtract the exponent. 12 minus 8 is 4. So that this division gives you 3 times 10 to the 4. And similarly for this calculation, except the exponent ends up negative. So that's a scientific notation. Just a very quick introduction for those of you who are not familiar with this. Okay. So now we can start evaluating how likely it is for stars to collide with each other, for galaxies to collide with each other. We need to talk about distances and size of objects. So we can talk about, let's try to put things in perspective and talk about how big is the Earth and how big is the Sun, and where are we in the universe. And so if I just give you these numbers, it's very boring, right? And it's actually very difficult to remember those numbers. So that this is not for you to remember, okay? You don't need to remember any of this. I want to give you the perspective, and the way to give you the perspective is actually to do a scaled model. Okay, so we want to scale down the universe into something that we actually are familiar with. Because those large numbers, they're too large. We are not familiar with those large numbers, and we don't really know how large they are. What is 1 followed by 9 zeros or 13 zeros? It's hard to tell. But we scale them down to things that we are familiar with, like this balloon, we can actually figure out, we can get an idea of how things are. So we are going to do a scaled model. We scale the universe down to smaller size. And we'll start by shrinking the sun to the size of a basketball. Basketball has a standard, so that's why I use basketball. But I couldn't find a basketball. The only thing I can find is this watermelon balloon, okay? But it's about the size of basketball, so that's fine. So let's just say that you scale down the sun to the size of this balloon. How big would the Earth be? What do you think? When you do a scaled model, you have to scale things down proportionally, right? By that I mean that if you scale down the whole thing, if the sun was twice as big as Earth, when in your scaled model, it should also be twice as big. But sun is not twice as big as the Earth, it's actually much bigger. What is the size of the Earth in the scaled model? Can you make a guess? Is it about the size of a tennis ball, or is it about the size of a ping pong ball? Or is it about the size of a grape? Or a grain of rice, tiny? Or is it like the thickness of our hair? Raise your card to show me your guess. Which one do you think is Earth? Is this tennis ball size thing, or ping pong ball size thing, or rice? I see green, yellow, orange, and white. No pink. Okay, tennis ball is ruled out, but all the other things have some chance to be right, according to you. So let's do this calculation. And how do we scale it down? The way we scale it down, as I said, it has to go down proportionally, right? Whatever is the ratio in the model has to be the same ratio as it is in the real world, in reality. In reality, if you take the ratio between the diameter of the Earth to the diameter of the sun, it has to equal what you have in the models. And that is how we do it. So all these numbers we know, and you can look it up in books and then plug it in. And the model diameter of the sun, let's say it's about 24 centimeters. That's the size of the basketball or this balloon. and what will be the model diameter of the Earth. And you can actually do this calculation. You don't have to do it now. Actually doing it for you. And we plug in those numbers. Diameter of the Earth is 13,000 kilometers, and that's 1.3 times 10 to the 4. And diameter of the Sun is 1.4 million kilometers. And then you divide those and times 24 centimeters. That ratio is very close to 1 to 100. So I'm just going to approximate it to 1 to 100. 1.3 and 1.4 are very close. So we don't have to be super accurate. We just get a rough sense of order of magnitude is fine. And so this is 10 to the 4 divided by 10 to the 6. And so you have 2 more zeros in the denominator. So that's 1 over 100 times 24 centimeter. And that's 0.24 centimeter. That is about 2 millimeters, about that big. So if this is the Sun, the Earth is about the size of a grain of rice. That is how small our Earth is compared to the Sun. Okay, that is actually scaled model. So the things that you often see in textbooks, where they do the Sun this big and then the Earth this big, those are not correct picture. You really want to draw the correct picture of how small the Earth compared to the Sun. You have to draw the Earth just like a dot compared to a basketball. That's how big it is. How big a contrast there it is. The Sun is much bigger than our Earth. So the correct answer is a grain of rice. Some of you got it right. But anyway, that is how small the Earth is compared to the Sun. And now let's see how far away do we have to place this grain of rice compared to the Sun. If this is the Sun, and that in our scaled model, where should we place this grain of rice so that it is more like the real thing in the solar system? And how do we calculate that? And we can just simply calculate that in the same way using this ratio thing. Take the Sun-Earth distance, divide by the diameter of the Sun in reality, and that is what it is in the models, right? And I'm going to just show you that calculation. And again, some numbers are very close. And this is the Sun-Earth distance is 1.5 times 10 to the 8 kilometer. And this diameter of the Sun is 1.4 times 10 to the 6. 1.5 and 1.4 are about the same thing. And so this is about 100 times bigger. So the Sun-Earth distance is about 100 times bigger than the size of the Sun. And so it's actually about 26 meters away. Where is 26 meters? Where should I place that grain of rice if this is the Sun? The Sun is sitting here. Our classroom is probably not big enough. This is about 10 meters from here to the back of the room. We actually have to place it out on the street. That is how far away the Earth is, which is in our model is not just a grain of rice. It's all within this basketball from about 26 meters away out on the street. Draw a huge circle around it. And so if we have scaled down the solar system to this, that is how far away the Earth is from the Sun. Okay, as you can see, it's actually really, really far. And our Earth is really, really tiny. That's what I want to show you in this scaled model. And what about other planets? Here you can see a table of where they will be in this scaled model. And you can see all the planets are tiny. They're all just a few millimeters big, less than a centimeter. The only exceptions are the outer planets. Jupiter is about the size. So this is how Jupiter is compared to the Sun. It's about an inch in diameter, or 2.4 centimeters. Saturn is about the same size, a little smaller. And Uranus and Neptune is about half of this. And that is how small they are, the planets are compared to the Sun. And where are they? The Mercury is close, is inside this classroom. So it's probably from the distance, it's about 10 meters away from the basketball. So from the basketball sun, and it is actually about 10 meters, yeah, in about the size of the classroom. Venus is a little further, and Earth is all on the street. And Mars is even further away, probably the next building. That's where Mars is. And Jupiter is even further. Saturn, Uranus, they're several hundreds meters away. Let's see, where is Neptune? Where is Neptune? 700 meters away. How big is 700 meters? You probably have taken some PE classes in high school, so you know how long it takes for you to run 800 meters, right? That's, where is it? This is where we are in ISRD building. 770 meters away is about the distance to New Asia College. That is the distance. So here is the sun, scaled down to the size of a balloon, and Neptune will be a New Asia College. And it's also just half the size of a ping pong ball. That's how far Neptune is in this scaled model. And throughout the solar system, you can see that it's about the size of the twice as big or 4 times as big as our campus. Our solar system, if you put the solar system into our CUHK campus, the sun will be this big, and then there are a few grains of rice next to it on the street in another building, and there's a couple ping pong balls and nothing else. All the asteroids, they're even tinier. They're just like dust. And then in the solar system, that's all. That's all there is. A balloon, a few grains of rice, and a couple ping pong balls out there in the area of the CUHK campus, and nothing else. And that is how empty our solar system is. It's very, very empty, right? There's nothing else. It's just a bunch of these tiny things. That is how empty the universe is, actually. So if the sun is, so let's continue. Now I told you that our sun is only one of the hundreds of billions of stars in the Milky Way. Where would our nearest stars to us be? The star that is nearest to our sun is about 4 light years away, and that is called Proxima Centauri. It's a star that you can see in the southern hemisphere. We cannot see it from here. And it's far away from us. It's 4 times 10 to the 13 kilometers. But we can't imagine that those are numbers. So let's still put it into perspective. Where would the next star be? The nearest star to our solar system. So here is a question for you. Where do you think we should put the next star? If the sun is shrink to the size of this balloon, where would the Proxima Centauri? You can calculate it, or you can just make a guess and then raise your card. Just make a guess, don't calculate. How far away would that be? Would it be Victoria Harbour, Macau, Shanghai, Singapore, or even further away? Singapore is already pretty far, right? I mean, don't get influenced by me, by what I'm saying. I see some orange, I see some green and yellow. Yeah, Macau is already kind of far, right? And Shanghai is even further. Okay, let's see. I'm going to tell you the answer right now. It's even further away. Even Singapore is not far away enough for this scaled model. So if we shrink the sun to the size of a basketball, even the nearest star will be even further away than Singapore. And where would that be? You have to go to Australia to find the next star. And it's actually about the same distance to Brisbane, Australia, or Sydney. Sydney is a little further away, so I chose Brisbane. It's about right. It's about 6,900 kilometers away. And that is where the next star will be.
we shrink the universe down by a huge factor already. We have already shrink the universe down by a huge factor. The size is gigantic. And we have shrunk it to the size of a basketball. Our Earth is a tiny grain of rice. And then in this model, the next star would be in Australia. And that is how far away there is. And that is actually the nearest star to us. There's no other stars nearer to us than that. And so we are actually very lonely in the universe. Imagine that on this scaled down universe, that's about the same size as the Earth, right? There's nothing beyond our CUHK campus, right? Our whole solar system is now shrink to the size of our campus, right? That's where Neptune's orbit is. It's about the distance from here to New Asia College. That's our solar system. Beyond the solar system, nothing in this huge area until you reach Australia. Then you have the next star. And that is how small stars are compared to how wide they separate. And how big is a star? The star is the size of a basketball. So how widely separated our stars are in the universe, in our galaxy? It's like two basketballs separated by the distance between Hong Kong and Brisbane, Australia. So that's about 7,000 kilometers. And it will probably take you around 5 or 6 hours to fly the distance, right? Airplanes have to fly 7 hours to get there. So that is how far away things are. And for these two basketballs to collide, do you think it's very likely? No, right? It's so ridiculously unlikely. That is so tiny compared to the separation between it. So that's how empty our universe is and how lonely we are. So the solar system is very isolated from other stars, and space is very empty of stars, like basketballs, thousands of kilometers apart. That is how empty it is. And even in star clusters, you may say, okay, we don't live in a star cluster. We don't have other stars nearby, and the nearest star is that far away as Australia. What about a star cluster? If I live in a star cluster, it'll be a little closer, but still probably at the distance of Shanghai or something. Right? It's not going to be much closer, more like a distance between Hong Kong and Macau. And still, the two basketballs will be separated like the distance between Hong Kong and Macau, and it's still at least tens of kilometers away in that scale model. And it's still very, very difficult for them to collide. Stars almost never collide with each other, unless the two stars are born together, unless the two stars were actually born in the same birth cloud, and they were just orbiting each other to start. If they were born independently in different places, they almost never collide. Okay, stars will almost never collide. What about the size of our galaxy and the distance to other galaxies? I think I already exceeded the time of the class. Maybe we should end today here, and so that since my fault to start the class late, but let's stop here, and then we'll continue on Thursday. Thank you very much. And I think check your registry to figure out where the classroom is for Thursday. I know I'm not completely sure anymore.